Hello, and thank you for coming to SIG School Scholars. Today, we're going to be looking at banked and unbanked curves. But before we move on from our study of vertical and horizontal circles, well, you might want to ponder the answer to this question. Because if you understand this, then you'll have a pretty good understanding of the circular motion. So you should think about that, and we'll discuss the answer at the end. So, let's go ahead and look at banked and unbanked curves. So, we're going to be looking at what happens when a car tries to round a curve. That's what we mean by a banked curve. By a curve. When the car rounds the curve on a flat surface, flat ground, then it's unbanked. However, when the road is raised at an angle as the car is turning, that is banked. And the angle of elevation is the banking angle. Okay, first we're going to look at an unbanked turn. Then we'll look at perfectly banked and then banked. So, say you have a car of mass 1,500 kilograms, okay, and it's traveling at a velocity of 20 meters per second, and the radius of the curve it's traveling around is 60 meters. The question is, will the car follow the curve if mu s equals 0.75? So, in the case of an unbanked curve, the radial force is supplied wholly by friction. However, if the force of friction is less than the radial force required to round the curve, around a curve of a given velocity, with a velocity v and a curve of radius r, okay, if this force of friction is less than the radial force that's required to do this, then we'll have no. The car will not, and it will skid. No. Maybe we should write this one. We'll have yes, skid. If the force of friction is greater than or equal to the radial force required to round the given curve at that velocity, then we'll have no skid. So, then let's go ahead and get started solving this problem. So what we're going to need to do is find the maximum force of friction that the pavement can provide, and that is just going to be the force of friction, which is going to be that mu s Fn. And in this case, because the ground is flat, Fn is mg. So we put that into our calculators. You get 0.75 times mass was 1,500 times 9.80. The maximum force of friction we can extract from the pavement will be 11,025. Let's say we got three significant figures, 60.0, 20.0. So we'll write 11.0 times 10 to the fourth newtons. This is going to be again toward the center. Oh wow, I made a small error. 1.10 times 10 to the fourth newtons. So now we're going to see what radial force is required. If the radial force is less than or equal to the friction, then, well, the car will not skid. If it's greater than the friction, then the car will definitely skid. And, okay, this is mv squared over r, of course. And that will be mass of 1500 times square of the velocity, which was 20, divided by r of 60, I believe it was. Yes. What we get is 10,000. Let's say we got two significant figures from our mass. So we'll say 1.0 times 10 to the fourth newtons. So obviously, force friction will be enough, and this car will not skid. It will not skid. Now, how about we determine the maximum velocity this car can travel going around this curve? Let's do that. Well, we know that force friction. This is the maximum force of friction that we can get. So what we'll do is we'll set that equal to our radial force and solve for velocity. What we get is velocity equals force friction times r divided by m, take the square root. We rearrange the terms. So when we put this into our calculators, let's see, by 1500. So, oh wow, that's interesting. It comes out as exactly 21. Well, no, we had two significant figures from the mass, we're saying. So 21 meters per second, exactly. So, that is the maximum velocity the car can round that curve with. Now, what happens if it starts to snow or rains or precipitates in some way? We know that this is the force that we must have, to round this curve with that velocity. But what if here the force radial is 10,000 newtons, but what if our mu-s, okay, yeah, it starts to precipitate somehow, well, some way, either snows or rains, hails, whatever, and the mu-s decreases to, let's say, from 0.75, it decreases all the way down to 0.30. What will happen now? So, remember, this was 10,000 newtons. Well, force friction will now be that new mu-s times mg, which will be 9.80 times 1500 times 0.30, and we get an insignificant 4,410 newtons of force, which will be nowhere near enough, which is why people slow down in icy conditions. Why you should slow down in icy conditions anyway. Not everybody does it. But, yes. So if you're still traveling at that same speed trying to round that curve, you would not do well. You would definitely skid. Would not go well. So, what then? The natural question would be to ask, what's the maximum velocity we can travel at? Well, of course, we'll do the same thing we did last time. Solve for this new v. Same formula. We should get quite a different answer. Yeah, it's much, much smaller. Oh, wait, no, it doesn't come out much smaller. Because we're taking a square root. 13, again, two significant figures, meters per second. Which isn't too much of a decrease. Well, it is it's like a 30% decrease or so. Well, around 40% decrease, because the force of friction decreased by quite a bit. Wait, let's see. Huh. Well, that's interesting. The ratio of the old force of friction and the new force of friction, the new over the old is 0.4, and the ratio of the old velocity under the new velocity is 0.62. So they are it shows about the same thing, that a 40% decrease in the mu led to approximately a 40% decrease in velocity. So now we're going to look at the case in which we have perfectly banked curve. So what that means is that, well, when we're rounding this curve, okay, so the banking of curves reduces the chance that skidding will occur. The reason why is because it reduces the reliance on friction. Because before, you had an unbanked curve, you're totally reliant upon friction. This is the only force acting in that direction. Now, in case of a banked curve, the force is not only friction, or it may, in the case of a perfectly banked curve, it's not friction at all. There's no friction acting. Reduces our reliance upon friction. The reason why that's a good thing is because the friction coefficient can be somewhat unreliable. We can't always guarantee it'll be high enough to allow safe driving at most speeds. So we bank curves sometimes, so that a car traveling will have another force, Fn sine theta, acting. Oh, that's not really good. Should be equal to Fn cosine theta. There, mg. So, basically, when this is perfectly banked, Fn sine theta equals mv squared over r. Now, how about we find a formula for theta? What we're about to find is a formula for theta, the angle at which the curve will be perfectly banked, if we know for a certain velocity on a curve of a given radius. So we know Fn cosine theta equals mg in this case. So Fn equals mg over the cosine of theta. So when we plug this back into our original equation, we get mg times the sine over the cosine of theta. Sine over cosine is tangent. That's equal to mv squared over r. Cancel out masses. G tangent theta equals v squared over r. And finally, tangent theta is v squared over rg. And we take the inverse tangent of v squared over rg, or gr, gives us theta. The angle that a curve will be perfectly banked at if that curve has a radius r, and we're talking about it being perfectly banked when a car travels, like I guess a car, doesn't really matter, travels at velocity v. So that is the case of perfectly banked. So now what we're going to look at is the very, well, I'm not sure what word to call it. I would think the most accurate term to describe what we're about to look at, probably disturbing. I would say disturbing. Maybe, yeah, disturbing. Or disgusting. That might be an even better word. You'll see. So, the problem comes when we have a curve that is not perfectly banked, because the velocity of the car is not equal to the velocity that, for that angle and for that radius. The velocity is either greater than that. Yeah, is greater than that, basically. When it's not perfectly banked, meaning that Fn sine theta is not sufficient to provide all of the radial force. It's just not large enough. And what we have is we have Fn sine theta as well as friction acting downslope. The components of that friction will be here. Fr sine theta, Fr cosine theta, and yeah, that looks good. So now, to understand this, we're going to do a problem. Now, let's erase this down here first, and then we'll do our problem. So this here is the case where Fn sine theta is not sufficient. Oh, I forgot to draw that one in. Thought I was forgetting something. So Fn sine theta and F FR cosine theta acting in the same direction. This is theta. So, this is the case when Fn sine theta is less than mv squared over r. Therefore, we must have friction. However, we didn't say that banked curves necessarily get rid of the need for friction. They reduce our reliance on friction. So basically, when you design a highway, you design it so that the speed limit, or design a curve, a curve, so that the speed limit keeps it so that the centripetal acceleration required to keep you following that curve can be provided by friction in the case of a unbanked curve, or friction plus Fn sine theta in the case of a banked curve. So you pick a speed limit of a velocity that can be, where this curve can be taken. So, let's see, the radius of a curve is 88 meters. If a curve with that radius is perfectly banked for a car traveling at 75 kilometers per hour, let's go ahead and change that to meters per second by dividing by 3.6 to give us 20.83 meters per second. What must be the coefficient of static friction for the car not for there to be if no skid at, let's divide 95 by 3.6, no skid at 26.39 meters per second. So this already looks like it's going to be very fun, because we're doing a banked curve and there's friction involved. So they said it's perfectly banked for at this velocity and that radius. So we'll apply that formula first. Let's write small. So we're going to need the space. Apply that theta equals inverse tangent of v squared over gr, and we'll plug in, so theta equals inverse tangent of v squared, 20.83 repeating, divided by 9.80 divided by 88. So theta is 26.72 degrees. So that is theta. Now, based upon this is the force diagram for this. So let's draw for the y first. Why not? Okay, so moving on. Fn cosine theta minus mg minus, and we have force of friction times sine of theta equals 0. Oh, whoops. Sum of forces in the x will be, so now we set these two equal to each other, and we're going to solve for mu, and that leads to only one unknown, and that unknown is mu, because we know theta, we know v, what's up there, we know the mass, right? Oh, the mass will cancel out, so it's not important. We know r. So yeah, we know everything. So v squared over r times mu cosine theta plus sine theta equals isn't really gonna fit. Okay, I'll write it down here. G cosine theta mu sine theta. So what we're going to do is multiply the denominators of each one on both sides. We get v squared. Okay, v squared times cosine of theta minus mu sine theta equals g r mu cosine theta plus sine theta. And what we do is we would distribute the gr and v squared and get mu on both sides and, you know, isolate it and everything. And that would give us our answer. Okay. At this point, I mean, this problem is just really involved. We've done most of the work, and most of the thinking work anyway. It's the really hard part. The harder part was just figuring out what needed to be done from drawing the force diagrams. And once you get to this point, it becomes pretty straightforward. Okay, so that is how you do a problem with a banked curve that is not perfectly banked. So the question I asked at the beginning, I will give you the answer. So this is really interesting what happens. Well, I mean, it's a tumble dryer, so I mean, it's not too interesting, but it's interesting enough. Oh, wow. See, there has to be a circle tool here somewhere. No? Okay, never mind. Okay, anyway. It's just getting worse. Okay, so the clothes get to the top and they fall. Or near the top, they fall. So my question was, why do they fall? And is the velocity that they have larger for a heavier load than for a lighter load? So why do they fall away instead of being pressed against the dryer? The drum for the whole thing. Let's first answer the question of their velocity and then the mass thing. So what we know is that at the top, which is where they're falling, this is uniform circular motion. They're spinning at the same rate. It doesn't speed up at one point. The load is moving at the same speed the entire time throughout the cycle, throughout one revolution or rotation, I mean. So this is uniform circular motion, and our v squared over r at the top will equal mg. Okay, so no, not mg. Mg is a force. Weight. It's just going to be g. So v will equal the square root of gr, and this result is independent of mass. So that will answer the second part. Doesn't matter for light load, if it's a light load or a heavy load. It's just gonna work the same way. So they must fall away because what happens is that at the top, this is basically a centripetal force. Mg is their weight, is their centripetal force. And again, this mv squared over r will equal mg, and masses cancel. And we go back to this again. Our v equals square root of gr. It doesn't matter how heavy the load is. It's just based upon how large the gravitational acceleration is. 9.80. Yeah. So when it reaches the top, the centripetal force on the load is at its maximum. And what happens is that the clothes are no longer moving fast enough for that force. Okay, remember, the centripetal force is the force required to keep the object moving in a curved path. The thing, though, is that it is also, if it is too large, will cause the object to fall out of its path, and if it's too small, it won't stay in the path. In this case, the force is too large for the velocity, so it falls out of the path. It can't maintain that path because the velocity is too slow. If the clothes were made to speed up much faster, like maybe in a washing machine, it just spin much faster, they would be pressed to the sides of it, because the forces on the clothes in the tumble dryer are going to be much greater. And the velocity of the clothes in the tumble dryer will be much greater, and because it's much greater, they will have a larger inertia. Their larger inertia will mean that they will be wanting to follow a straight path, but so they are pushed against the sides of the container because of their inertia. So the answer is, well, the centripetal force, or acceleration, however you want to put it, is too large for the clothes to continue moving in a curved path at the top of the path, the circular path, when they're traveling at that velocity that they have in the tumble dryer. Okay. Thank you for watching the video. If you want us to make a video on a specific topic, just leave a comment either in the comment section below or on our website at sigschooltutors.wordpress.com, and we'll try to fulfill your request as soon as possible. Thanks.